Today we will be discussing design for forging. In this presentation, we will specifically focus on hot forging, as well as focusing on closed dies. We will be closely following the book Product Design for Manufacture and Assembly by Boothroyd and Dewhurst, with additional information from Manufacturing, Engineering, and Technology by Kalpakian and Schmidt. If you have any questions or would like more in-depth information, you can refer back to these texts. We will start with an overview of the forging process. Forging is a process of shaping a hot or cold metal, although we will not be discussing cold forging today. In hot forging, even though the temperature is elevated, the material is not melted. Instead, solid stock material is subjected to forces that deform the material repeatedly until it is in the desired form. These forces can be applied to simple open dies or more complex closed dies, which we will focus on today. While they are called closed dies, they do not close 100% of the way, as there is a gap at the edge of the die to allow for material overflow. A closed die can be seen here in the image on the left, where the blank is inserted into the die. It is then compressed in one stroke or under repeated blows until the material flows to the edges of the mold and fills the shape, with excess material being forced out the sides in what's called the flash. This process of material deformation presents an advantage over some other material processes, as it has a beneficial effect on the microstructure. During the deformation, the grain boundaries of the crystalline structure are forced along with the material, resulting in aligned, smaller grain boundaries and increased part toughness and strength. The picture on the right visualizes the resulting microstructure of different processes, the blue being casting, where the microstructure forms during cooling and is left unaffected, the orange machining, where the microstructure may be worked slightly, but the geometry is stamped out, and the green shows the aligned microstructure of forging. Forging is actually an ancient process, with many improvements made in modern times. Forging dates back to 4000 BC in Mesopotamia. Gold, bronze, and iron were all used in early forging processes. It has traditionally been used to make coins, jewelry, tools, and weapons. Forging has evolved from a simple process using a hammer and anvil into a high-tech industrial process used today. One of the key concepts in forging is flash. Flash is the extra material that gets forced out the edges of a mold at the parting line. It is essential in the forging process. As material reaches the edges of the mold, some is forced into the cracks of the parting line, and as the work continues, the load begins to climb. This forces material into the entire cavity. There is no more material being added as it is in casting or injection molding, so the extra material to drive up forces and completely fill the cavity must be present from the start. This excess material will escape the mold as flash. The more complex a part is, the higher the pressure needs to be to fully fill the mold. As a result of this, the more complex a part is, the more flash will be required. Flash can account for more than 50% of the final part volume. Webbing is another source of extra material that is not present in the final part. Webs are large, thin sections aligned with the direction of the die closure. They can add strength to a part and are required if there will be through holes in the part. The web fills the space of the hole and is removed during final processing. Material is also lost due to the oxidation of the metal throughout the forging process in what is called scale loss. This oxidation must be removed before the part is finished. The final step during forging is removal of the flash, webbing, and oxidation. Machining can be used for all three, but is a more expensive process. Alternatively, a trimming die can be used to shear off flash and pierce holes for webs. This is cheaper than machining and is done while the part is still hot. Another concept crucial to forging is preforming. Unlike castings or molding, where a liquid is poured directly into a mold of the final part shape, forging often requires 2 or more steps. Depending on the part complexity, a sequence of preforms may be required to reach the final shape. Simply using one mold would result in excessive flash or too high of loads required. On this slide, we have an example of 5 steps, from material blank to final part. The blank is how the material is received or purchased and is a generic shape. In this sequence, there are 2 preforming steps before the finishing mold. During edging, the material begins to take a rough shape, but is not overly different from the blank. The next step, blocking, adds a smoothed out version of the final details. Then the part is ready for the finishing step where the details are fully embodied, and the trimming step to remove the flash. This brings us to dies. Dies are used to shape the material in each forging step. If the parts are small enough, several or all of the preform and finishing impressions may be incorporated into one die. If this is done, they must be arranged to minimize the size of the die while ensuring they are adequately spaced. Another factor in die design is the parting line. Flat, simple parting lines are preferred, and if the parting line becomes complicated, die locks may be added to prevent mismatch. There is a wide range of equipment available to provide the force and compression needed for forges. Hammers are the most common, but presses are also prevalent. Here on the left, we can see an example of 4 types of hammers: board hammer, belt hammer, chain hammer, and airlift hammer. On the right are presses. We have a crank press, knuckle joint press, friction screw press, and hydraulic press. There are 2 categories the equipment falls into: work restricted or stroke restricted. For work restricted machines, like hammers and hydraulic presses, the amount of energy or force is the limiting factor. If this limit is an issue, multiple blows may be needed. For stroke resisted, the deformation per stroke becomes an issue. If there isn't enough force per stroke, a larger machine is required. Choice of machine depends both on the geometry and material of the forging and the attributes of the equipment. This selection is complicated, but some of the relevant data is presented here. Large quantity production rates may seek a higher average usable blow rate, or die closing speed may be selected based on the material strain rate sensitivity. For more tables and charts comparing equipment, please refer to Boothroyd. Forging is a process that involves deforming metals. Ductility is the key property for a material to be forgeable. Metals used in forging must be ductile enough to undergo deformation without cracking. Carbon and alloy steels are most commonly used. A list of materials used in forging, as well as the temperature they must be heated to for hot forging, are presented on the left of the slide. The temperature of hot forging is important as the higher temperature materials will require more energy in. The difficulty of forging these metals is captured by the load factor, which is measured in units of energy per area. More challenging materials require more energy to deform per unit area, which results in more energy cost and more expensive machines capable of providing the required energy. A selection of materials and their load factors are shown on the right side of the slide. Taking all of this into consideration, we are able to construct some design guidelines to design with forging in mind. First, we continue looking at material. Material should be selected in order to meet the design needs while trying to minimize cost during forging. The design of the part may require high strength, toughness, corrosion resistance, or wear resistance. The material will also have to be ductile enough to be forgeable. Next, the availability of the material should be considered. You want to be able to consistently acquire the stock material form that you will need based on your molds. Lastly, cost needs to be considered, both the cost of the stock material and the cost of processing. You should look for a material that is cheap to purchase and a material that will result in low processing costs, as will be discussed in the next section. There is a lot of room to design for forging when it comes to part geometry. The first guideline is to remove complexity. Complex geometries drive up cost and part failures. A complex geometry will require multiple preforms as well as more expensive finishing molds. Complexity also drives up processing costs. More complexity requires higher pressures, more energy, and more expensive machines. Next is size. The size of the part should be minimized. A larger part requires a larger, more expensive die. It also requires greater force during pressing. If the part can be made smaller, it will help to bring down the forces and the cost of the die. Parts should be designed to be symmetrical where possible. This helps with uniform cooling and are easier to forge. Uniform thickness is also desirable as it helps with cooling, which will help minimize warping. If the thickness does vary throughout the part, the thickness should be changed slowly and smoothly to avoid laps and folds. Additionally, thin sections should try to be avoided as they restrict material flow. Draft angle should be added where possible. This helps with removing the part from the die. If the part sticks to the mold, it can cause tears or deformation. This can also affect the die, as this damage can occur to the die itself and shorten the lifespan of an expensive die. Corners should be rounded and sharp points should be avoided. Round corners help the material flow and are easier to fill. Sharp corners can prevent material flow and can also cause stress concentrations in the final part that can lead to cracking. Sharp corners can also increase wear in the die. Recommended corner and fillet radii can be found in the table at the right of the slide. The parting line of the die should be kept flat and simple. A cranked parting line can cause mold misalignment and add handling complexity. To avoid this misalignment, die locks need to be added in, which drive up die complexity and weight, both of which increase cost. Tolerances, including surface finish tolerances, should be kept loose where possible to avoid costly machining steps added at the end of the process to meet the strict tolerances. A chart showing recommended surface finish based on material and relative forging size can be found at the right of the slide. Machining allowances should be added in to permit machining on mating surfaces or parts requiring precise surface finish. These surfaces should be built up so that the material removal doesn't drive the part out of tolerance. Additional machining may be needed on flash and web geometry or oxidized surfaces and should be added into the machining allowances. Allowances should also be added for part shrinkage. As the part cools, it will contract some amount depending on the material properties. The part should be designed slightly oversized to account for this shrinkage. Lastly, we examine a cost model for forging. Since today we are discussing hot forging, the estimates presented here are only for conventional dies and parts made with hammers or forging presses. Materials have the largest contribution to forging cost, at about 50%. Unfortunately, due to factors discussed such as flash, a lot of the material cost ends up being waste. Dies come in at about 10% of the cost, though this will change depending on complexity and how many total pieces are made. The rest of the cost comes from factors like labor, equipment operating, overhead, flash removal, and other processing of the part. For early estimates, the cost is broken into three main parts that are added up for the total cost: materials, processing, and die creation. Evaluating the material cost is the easiest portion of this initial estimate. Material cost can be estimated with one equation, which you see in front of you. This is essentially just a cost per weight multiplied by the total mass of the part. Finding the total mass used is a bit complicated due to all of the extra material that goes into forging, but you can see the main volume of the part, the end volume of the flash, and materials used in the webbings is all accounted for. Additionally, scale loss, the material removed due to oxidation that occurs during the process, is added in. This final total part volume is multiplied by the density to find the mass of material used, then finally by the cost per weight. Calculating the operating cost is a bit more complicated. There are a lot more equations and variables, so we're not going to go too in depth here, but if you want to perform the calculations, you can follow along in Boothroyd. The first portion of operating cost is based on the equipment. First, you look at the production cost per piece, which is just the operating cost, which includes labor and handling in addition to the equipment, times the production rate. The production rate can further be broken down into how many blows it takes times the rate the blows are delivered. This will depend on what machine is used, so that needs to be selected early on. You can use the tables and charts in the book to select correct machines based on the material and part complexity you have. You will also need to account for the energy capacity, which is determined from part area, material load factor, and shape load factor. Again, there are a lot of variables, so instead of going into each one, I'm going to refer you to Boothroyd. Next, we look at the forging processing cost. Again, the first part involves looking at the cost rate, now per operation, and multiplying it by the number of operations needed and the number of identical forgings per cycle. This second equation here is a handy estimation to give cost per operation. You compare the relative cost compared to a 1,000 pound hammer and multiply it by the cost of operating the 1,000 pound hammer. Last, we look at the setup cost, which really just breaks down to cost rate multiplied by the batch size and setup time. The setup time can be estimated from energy capacity in this equation at the very bottom. The last portion of our cost estimate comes from the cost of the die. This is a very involved process, so for now we're just going to discuss the factors that go into this part of the estimation. The cost of the die breaks into two main pieces: the cost of the die material and the cost of the labor that goes into the machining of the die. The first thing that affects the die price is the number of cavities. As we discussed previously, forging often requires preforming, so there will be multiple cavities for the busters, pre-blockers, etc. Depending on the part, these may all be in one die, or there may be multiple. This will affect the size of the die and how much material is used, as well as the complexity of machining required. Once you have your die layout, you can use your geometry, so width, length, and depth, to figure out the size of the die and resulting die material cost. Next, you have to look at the time that goes into creating the die. This includes a whole slew of factors, including the time for initial preparation of the block, the time for laying it out, time for milling, bench work, and any other subsequent operations that may result from the complexity, size, and shape of your die. This all goes into the die cost, but the last thing that has to be factored in is life. There's a lot of wear and tear on these dies, and they don't last forever. If your production run is smaller than the die life, that's simple. If the run is greater than your die life, you have to factor in the cost of refurbishing and resinking dies, and eventually replacing the entire die when it can't be further repaired. Taking your cost estimate for your die and adding it to production cost and material cost, you have an initial estimate for your forging cost. To revisit what we've talked about today, forging is a manufacturing method that involves deforming, not melting, metal into desired part geometries. This method leads to good toughness and strength, but does create a lot of wasted material via flash and webs. multiple die may be needed to complete the necessary preforming. There is a wide selection of machines to select from to perform the process, but a narrower selection of materials that are able to be worked without cracking. Design guidelines should be followed to optimize material, part geometry, and tolerances, and cost can be estimated based on materials, processing, and die cost. As mentioned at the beginning of this presentation, most of the information today came from product design for manufacture and assembly by Boothroyd and Dewhurst, and manufacturing engineering and technology by Kalpakjian and Schmidt, with some additional information from these references.